Hello, class. I thought that I would do another lecture, sort of put a nice lecture together, I feel, on electric fields, capacitors. What is a capacitor? How does this thing all work and everything else? And how are the equations working? So, capacitors and capacitance. Anyway. Let's think a little bit about the equations and the relationships between the various variables that we have, right? So we have flux, and flux is usually charge, right? That's what charge is, flux, and I'll call this flux. We know that flux divided by area is going to be my flux density, right? So flux density is flux divided by cross-sectional area. And so, of course, that would be in coulombs per square meter, right? When we think of the electric field, we know that force equals the electric field times whatever charge we're going to put in that electric field, right? In fact, why don't I keep charge, when I refer to charge on this formula page, why don't I keep charge always the same so that you aren't confused with me using a large Q and a small q. So I'll say that charge is a large Q for what we're doing on this page here. Okay. So if that's true, then that means that my electric field is going to be force divided by charge, right? In fact, I could say that that was force divided by charge, or we could say that it is, well, I'll say it's two things. It's newtons per coulomb, but we know a newton per coulomb is also a volt per meter, which also explains the, way an electric field is laid out. Here's another equation that I'm sure you've used before in Network Theory 1 and Network Theory 2 probably. Let me just box off some of these equations because we're going to have quite a few equations that I'm going to be writing up here. All right. So let's keep going. So how about, I'll start here. C equals Q over V. And that's really the equation. I'm going to put a star next to that. That's really the equation that we're going to be focusing on in today's lecture, right? Capacitance equals charge divided by unit volume. 1 coulomb equals, oh wait a second, 1 coulomb per volt is going to equal 1 farad, right? So let's look at a couple other things too, because we also know that D equals epsilon E, don't we? Well, then that would mean that epsilon equals D over E, right? But we know what D is, right? D is flux. D is flux. Oh, wait. That's not, D is D's flux density. Sorry, I got it here. There's D. So D, of course, is flux density. And that would be charge, or, over area. And then that would also be divided by, I wrote this the wrong way, but V over D, because that is what E is. Now let me rewrite this again so that it looks better. Q over A divided by V over D. Why do we know it's V over D? Because isn't that volts per meter? Isn't that voltage over the distance? Remember the electron gun that we talked about a long time ago? Right, so that's what an electric field is. V divided by D. Okay, so if we have that, then we can rationalize that fraction. And we can say that that fraction really is QD, where am I? Yeah, QD over VA. Right. QD over VA. Hey, you know, I see something in there, don't I? Let's go back down here. So epsilon then, if I just bring this back to here, Q over A, isn't that, oh wait, what have I, Q over V, isn't that equal to C? Right, Q over V equals C, so I've got Q over V here, so it's just really equal to C, the capacitance, times the thickness of the capacitance, divided by the cross-sectional area of the capacitance. All right. Now, what is this epsilon here? This is the epsilon of the dielectric. Epsilon equals permittivity of dielectric. Right? So the sandwich in between the two. Let me draw. Actually, I probably should draw it this way. Let me draw a capacitor over here. Right? So we've got a capacitor with 2 plates there. And I want to define some of the things that we're looking at here because we're using A. What is A? A is the cross-sectional area of that plate, right? And let's say that, you know, one side of the plate is, oh, what's D? D is just this distance here, right? The separation of the 2 copper plates in the capacitor. So that's basically the thickness of the dielectric right there, because everything in the middle of those 2 plates, as we know, is dielectric. If we don't come back in the fall, I'm getting more colored pens. Who knows what the future holds? I'll tell you what, if anybody asked me if I was going to be doing this for the summer semester, I would, you know, like 6 months ago, I would have said, "Are you crazy?" Anyway, let's go on because you're the only people I talk to, and I'm not even talking to anybody. So epsilon is the permittivity of the dielectric between the 2 plates that we have here. And then this is the equation. So don't think that epsilon, remember, let's write that down again. Epsilon equals epsilon sub r times epsilon sub o. Always remember that. Now, I want to go on and I want to look at some other relationships. Now that we know that relationship, I want to derive it a different way, right? So I derived it this way. Let me just put that down there. Now, let me derive that same relationship, right? If we know that C equals Q over V, right? So C equals Q over V. Well, what is Q? Q is just D times A, isn't it? D times A over V. What's D? It's just epsilon times E times A divided by V. what's V? So we've got epsilon E, A in the numerator, and what's V? V is E times D, isn't it? Right? So the E's cancel out, and I get epsilon times A over D. So basically the same relationship, but just coming at it from different angles using the equations, the base equations that I've got up here, up there on top of you. All right. I'm going to go. I'll go through a couple more of these just to look at them because, well, D over epsilon equals E, the electric field. And what is epsilon? Isn't that what we had up here, just C times D over A? So wouldn't this just be A times D over C times small d? Right, so that's what the electric fields would be. And again, all of these are just algebraic manipulations of the same equations that I've already put up there. I could look at that in the same way. When we say that I've got D, then isn't really D just Q over A? In fact, why don't I do that? So A times and D is just, oh, wait a second. Yeah, Q over A CD, right? Because D is just Q over A. So the A's will cancel out. And I hope we did that right. Let's see, Q over A CD. And then that would be A times, now Q would be CV, ACV over, wait a second, ACV, because that's Q over A, DQ over A, yep. I'm just trying to see if I can get the CV, and then, where have I, oh, yeah, no, that's right. Over ACD and the C, so CV over CD. Don't I already have that someplace? CV over C, let me just check. Yep, that's right. That is right. And then I could also say, so CV over CD, let's just keep going with this one. E equals CV over CD. And then CD, if we look up here, equals epsilon A. So it also equals CV over epsilon A. Again, all the same equations that I'm working with here. I'm going to get into some more interesting ones later on. But these are all just so many different ways that you can, manipulate these things. So I want to keep doing them for a little while. We're going to get into other more interesting things, but I found these to be very useful. Very, a lot of people. I'm sure you can all do the algebra. Let's all do it together. So V is just E times D, right? Which would be Q D over epsilon A, right? because E, as we know from over here, must be Q over epsilon A someplace in here, right? No, I don't see it anywhere. Wait, no, that's V. So yeah, no wonder it wouldn't be that. Okay. Well, the rest of them all seem pretty much the same. So what I want to do now, I'll do one more. I've got one more here. I think that was sort of an interesting little one. What is it with E? E equals Q over epsilon A equals CV over epsilon A. Is that right? Let's see. D, yep. So that's just another one. But what I really want to look at now, I'm going to close that box. I'll use that for something later. But what I really want to look at now, excuse me, is I want to look at energy. So let's look at the energy that can be contained inside a capacitor. And isn't energy force times distance, right? Energy is force times distance. So what is force? Well, isn't force just a small amount of charge times the electric field, right? Isn't that what force is? What have I got? Force equals the electric field times charge, right? So I'm just saying I've just got a small amount of charge that's there. Okay, and then that is times D. But hey, wait a second. What is E times D? Isn't that V? You can see that in the thing up here. Why don't I just put that up there? E times D equals V, although you can see it in the algebraic working I've done with all the equations anyway. And then let's go back to this. So if E times D, then that really means that's voltage times that small charge Q, doesn't it? Well, why don't we integrate over that, right? So if we want to take, that would just be, in other words, what I've got here is just a differential amount of force, differential amount of energy. And what I want to look at is what is the total energy, right? So I'm going to integrate this from 0 to Q, V dq, right? Isn't that what I've got here? Isn't that V dq? So that's what I'm going to do. All right, well, what we know from the equation we have up here is that V actually equals Q divided by C, doesn't it? So from 0 to Q of Q divided by C dq, right? And then Q divided by C, well, 1 over C, we can take that outside of the equation. I think everybody can see that. And then all we're going to really do is just integrate Q dq, and that's just Q squared over 2, right? Q squared over 2. So we've got Q squared over 2C evaluated between Q and 0. Right? So yeah, that's sort of ridiculous, but why don't I just write it there anyway again? Q squared over 2C. Now, let's replace Q squared. So we know that's going to be C squared over times V squared over 2C. And then let's cancel the C's out, right? We can cancel this C out with one of those C's. So that's CV squared over 2. And of course, we know that, don't we? We know that as capacitive energy. That is the energy that you probably learned in Circuit Theory 1 is stored inside a capacitor. Now I want to take this a little bit further when we think about energy. And say, okay, well, it's CV squared over 2. That makes sense. So that would be 1/2 C. So C is going to be epsilon A over D, right? Epsilon A over D, that's what C is. And then V squared, well, we know that V is just electric field times distance. And I'll just go ahead and square both of those right off the bat. Okay. So what that ends up giving us is 1/2 epsilon E, the electric field magnitude squared, times the cross-sectional area times the distance. And in fact, what is the cross-sectional area times the distance? Isn't that the volume of the dielectric? Right? That's the volume of the dielectric. So this would be the energy that is contained in the electric field inside the capacitor. There's the permittivity of the dielectric, the electric field strength inside the dielectric times the cross-sectional area of the dielectric and D, right? And so as you can see from this, how can I increase the amount of energy per electric field that I put inside that thing? How about E? How about E? How about increasing E? Right? You could do that. Now, on the other hand, there's some materials that have a very high E, but they have a very low electric field breakdown strength. And that low electric field breakdown strength is going to determine what D minimum is, right? Because if we get those too close, it's going to fry. Lightning is going to fly through that dielectric. So we can't get them too close. And so the dielectric strength or dielectric breakdown strength, so our maximum E, you know, that's all going to play a role in it. And I want to look, the next lecture we're going to do, I want to look at a comparison. What was, just a second. I thought somebody was knocking at the door. They weren't. It's my isolation delusion that someone will actually come and deliver a package or something. I don't know. I'm ordering things just so people show up, but then there's only the package there. There's never a human. I'm kidding. Of course, I have a lot of people that live around me and stuff. But okay, now, what would this be in? Right? This is energy, right? So this is joules. Now, what if instead I wanted energy to find out what was the energy per unit volume? That's important, isn't it? I mean, if we had to use lead acid batteries, could we ever have electric cars? They sure wouldn't be like electric cars are nowadays, would they? So that's right. So energy per unit volume is very important. And that's why I said that's volume. So the comparison thing here is 1/2 epsilon E squared. That's where you'll find out. And what are these units? These units would be pascals, wouldn't they? Right? So there you go. I have no real idea how long that's been. I think it's been about 25 minutes, actually. What I want to do next in the next lecture is I want to do a comparison example between using mica, which is a very low permittivity, high a dielectric breakdown strength material, and I want to compare that. Come on. And I want to compare that to strontium titanate, which is a super high permittivity, but low dielectric breakdown strength material. Okay. All right. So we'll, I don't know when I'm going to do that. Might not be right now.